Question 1 gives an object moves along a straight line with the velocity v of t equals t squared minus 4t plus 3 from the interval of 0 to 5. The first question asks you to find all times in 0 to 5 when the object changes direction. In your explanation, clearly state what it means for the object to change direction in terms of the sign v of t. I said the object changes direction at x equals 1 and x equals 3. Because this is where the velocity becomes 0, meaning the object has come to a stop. And then plugging in values after and before these points reveals a sign change. Since velocity is a vector, this means that the direction changes at these points. I found these values by equating t squared minus 4t plus 3 to 0, ending up with the equation x minus 3 times x minus 1 equals 0. This gives you the values x equals 1 and x equals 3. And if you plug these back into these equations at a value such as x equals negative 2, and a value x equals 0, or a value x equals 2, or a value x equals 4, you get values to where they are either higher or they're either positive or negative. For B, compute the displacement of the object on the interval 0 to 5. Write your answers as an exact value. I put in the interval 0 to 5 the velocity equation d of t to get the value 20 over thirds. This is the displacement because this is the total amount of distance you are from the initial position. For C, total distance travel, compute the total distance traveled in 0 to 5. Make sure to explain why you must split the interval if needed and show this setup using an absolute value. It is necessary to split the interval because to find the value for distance traveled, it needs to account for the distance retraced from the initial position or the negative distance in terms of the velocity vector. So to get this, you split up the interval into 0 to 1, 1 to 3, and 3 to 5, because from 1 to 3, the velocity vector is negative. Now, just because the velocity vector is negative does not mean you should account for this negative value because you are trying to get the total distance traveled, not the displacement. So you end up with 0 to 1, t squared minus 4t plus 3 dt, plus the absolute value of 1 to 3, t squared minus 4t dt, plus 3 to 5, t squared minus 4t plus 3 dt. For question 4, concept checked. In 1 of 3 sentences, explain why displacement can be 0 while total distance cannot be 0. I said displacement can be 0 while total distance cannot, because displacement is defined as the difference of the final position and the initial position, or more simply put, the distance traveled in reference to the initial position. For problem number 2, question number 1, sketch an intersection, sketch 3 curves, and clearly mark the region R. Find the intersection points, write your intersection points as ordered pairs. So here I have the region R and the intersection points as ordered pairs. I found these values by equating x squared minus 2, or by equating x squared minus 2 to x, and getting the values x minus 2 and x plus 1 equals 0, or x equals negative 2 and x equals 1. I then found the outer bounds of the total function for x by equating x squared minus 2 to 0 to get x positive and negative square root 2. This will be useful when doing the function in terms of x. So question number 2 says, why dy is simpler here? For some reason, setting up the area with dx requires splitting the integral into 2 parts, while using dy can be done with a single integral. Explain why for this region it is more natural and more compact to use horizontal slices, integrating with respect to y instead of vertical slices. In your explanation, make clear which curve is the left boundary and which is the right boundary. So I have said for this region, it is more natural to integrate in terms of y because in terms of x, I'm not sure what this is, for the functions change across the bounds for the bounds for the function changes across the interval, whereas in terms of y, there are consistent function bounds. So using horizontal slices, question 3, this kind of showcases what I'm talking about. You get the absolute value of negative 1 to 0, y minus square root y plus 2 dy, plus 0 to 2, the square root of y plus 2 minus y dy. This is the absolute value because you're trying to find the total area of the function, and negative 1 to 0 is in the is below the x-axis, making it negative. So to find the total area, you should have two positive values, adding them up together. And then I also, to explain my process in getting the horizontal slices, I have taken the right function and subtracted it from the left function across two separate intervals, which is why we have to split it up, but it's still not as much as using vertical slices. We have to split it up from -1 right here in terms of y to 0. And then our right function is y and our left function is the square root of y plus 2. And then across this interval, 0 to 2, our right function is the square root of y plus 2, and our left function is y. So using vertical slices, question number 4, we end up with a much more complicated integral, splitting the integral up into 4 different functions, because our function changes across the bound. When looking at this function vertically, we can see that from negative square root of 2, which I found earlier, to 1, the intersection from top down is different from 1 to 0. So we have to split it up across the region, not just across when the function changes after it crosses the y-axis. We have to actually do it across the region, so making it more complicated. And then this also happens at this other intersection. From top down, we have y equals x minus 0, and then at the intersection of 2, it switches to y equals x minus x squared minus 2. So we have to split the function up into 4 different integrals. This is much more complicated than the first horizontal slices, meaning we should probably most likely put the function in terms of y every time we see something similar to this. And then 5, compute the area. I don't know if I explained what I wrote here. The splits are necessary because the vertical bounds for the function changes across the region. So I did explain that. And then here I computed. I got the integral of these here to get this, using the absolute value again, into this, getting the exact value of 1/2 plus 4, the square root of 2 minus 2 over 3 plus 16 minus 4 times the square root of 2 over 3 minus 2. I believe putting this into a calculator and calculating it, you get something similar to 3.6 or something along those lines. I'm not sure. I didn't go that far. And then because we're getting the exact value. And then for problem number 3, let f of x equal the square root of x plus 1 and g of x equal x squared plus 1. Let R be the region bounded by the graphs of f and g on the interval 0 to 1. The region R is revolved about the vertical line x equals 2. Understand the region. First question, sketch y equals f of x and y equals g of x on 0 to 1. Find the intersection points on 0 to 1 and clearly indicate which curve is on top of this interval. So here we have A. I have sketched x squared plus 1, a simple squared equation. Adding 1 gives us a new y intersection at plus 1, and the same can be done for the square root of x plus 1. This gives us the region R bounded here. I have shaded it in, but I have also shaded the region in terms of y right here for when I did the washer method. And here we can see the intersection is at 1, 2, because the square root of 1 plus 1 equals 2, and 1 squared plus 1 equals 2. And we also have an intersection at 0, 0. That's less relevant, but it is our bounds. And we are revolving around the axis x equals 2. So the top curve is clearly the square root of x plus 1. And for method 1, washers, we are going to use horizontal slices, integrating with respect to y. Part A of question 1 asks us to write it in terms of y. Y equals the square root of x plus 1. Y equals x squared plus 1. We get y minus 1 squared equals x. The square root of y minus 1 equals x. This is necessary because to get a washer radius, you need to put it in terms of y. So we have pi 0 to 2 2 minus y minus 1 squared, or squared. Okay, I will go back and I'll say the reason why we need to put this in terms of y is because from here to here will be our washer radius, not up and down. That would be the washer's height. But we do not need the washer's height in this equation. Or I'm not sure if the washer's height is relevant at all, but the radius is much more important. So we get 0 to 2 pi 2 minus y minus 1 squared. This is because at 2 to 0, this full value is 2. And the reason why I have shaded this area right here is to showcase that this is the square root of, no, this is y minus 1 squared right here. And 2 minus this region equals this region right here. And we can see from this depiction that that is the larger radius for the washer, the total washer. And 2 minus this region right here, 2 minus this region, is the smaller radius of the washer. So we end up getting 2 minus y minus 1 squared, large R squared, minus 2 minus the square root of y minus 1, little r squared, dy, to get our full washer method. Now we're going to be moving to shells, the easier method in this equation, because simply said, the shell method is natural because the radius of the shell is always perpendicular to the axis of revolution. In simpler terms, and in this case, we revolve around x equals 2, and our function is already in terms of x, so no conversions need to be made. Now what I mean by the radius of the shell always being perpendicular to the axis of revolution is that if we have an axis here and we are revolving around this axis, we are always going to be having a radius across here. And if we are drawing a shell, which I have not drawn, we would be getting the radius of a shell equaling to x. So if this was in terms of y, and we were revolving around the y-axis, our shell's radius is always perpendicular, oh my gosh, to the axis of revolution. As you can see, now the radius would be y. So, and then the height of our shell is going to be the function, the region bounded by the functions. Because as you can see here, the height of the shell would be the region bounded, which we already are in terms of x. So top minus bottom, it's much simpler. 2 pi, 0 to 1, the radius times the height, the square root of x plus 1 minus x squared plus 1 d of x. The last question asks us in one of three sentences, explain why both methods must give the same volume, even though one uses dx and the other uses dy. And I said, both methods give the same volume because switching from dx to dy does not change anything about the function, only the perspective from which the calculation is being made, or you can, instead of saying perspective, you can say horizontal or vertical. So we're not changing anything about the function when we switch from dx to dy. We're changing how we look at the function. So if we were looking at the function in terms of y, we're looking at it horizontally. If we look at it in terms of x, we're looking at it vertically. We're not actually doing anything, we're just converting values that already exist. Okay, that is everything for video homework number 1.